So we're going to be finishing up the last part of chapter 8 here. We've been talking about empirical formulas and molecular formulas and really how to calculate both of them. So we're going to, again, review a little bit here at the beginning about calculating molecular formulas. So remember to calculate the molecular formula, there really is sort of three things that you need. The very first thing that you need is the empirical formula. So either the empirical formula would be given to you, or you might need to calculate it yourself. But you definitely need the empirical formula there to calculate the molecular formula. Remember that when we do calculate the empirical formula, like we've done previously, the first thing you really want to do is convert grams to moles. You then want to make sure that you divide by the smallest number of moles. Obviously, to convert grams to moles, we would use the molar mass from the periodic table. Once we divide by the smallest number of moles, if we do end up with all whole numbers when we do that, remember that that will basically give you your empirical formula. So for example, let's just say we did that though, and we did not end up with all whole numbers. Let's just say I've got A 1.5 and B 2 as my empirical formula after I divided by the smallest number of moles. The 1.5 is not good. Remember that the subscripts do need to be whole numbers. So we do need to find a factor to multiply that by, and in this case we could multiply it by 2, which would give us an empirical formula A3B4 in my example. Remember that we would multiply the 2 by everybody in the formula, not just the 1.5. Now, once you have the empirical formula, that's one of the first steps that you need to get to the molecular formula. The next thing that you need is the empirical formula's molar mass. And we go to the periodic table and add up the molar mass of everything that's present in our empirical formula. The last thing that we need is the approximate molar mass of the compound. The good news on that is typically a value that is given to you inside the problem. So usually somewhere in the problem, they'll say, hey, the approximate molar mass of the compound is this, or it has a range even of molar mass in terms of grams per mole, but they'll give you some piece of information about it. So what do we do with all this information? Well, we take the approximate molar mass of our compound. Again, that's going to be given to us in the problem. And we're going to divide that number by the molar mass of the empirical formula. So again, molar mass of a compound given to us in the problem divided by the molar mass of the empirical formula, which in most cases we would be calculating. This is going to give you an actual number here. And this number most likely will be a whole number. And it should be probably the factor that you need to multiply the empirical formula by to achieve the molecular formula. So let's just say, for example, here, we do have my empirical formula there that we had, which was our A3B4. And let's just say that the factor that we got when we did the molar mass of the compound divided by the empirical formula molar mass was 4. We would multiply that 4 by everybody in the empirical formula. And in this example would give us A12B16 as our molecular formula. So that would give us both the empirical formula and the molecular formula. And remember that the one place where you could do a little bit of rounding is there when we're figuring out that factor for the molecular formula. So let's take a look at an actual problem here. So in this problem, we have a compound that's composed of 1.52 grams of nitrogen and 3.47 grams of oxygen. The molar mass of this compound is between 90 and 95 grams per mole. So in this case, we actually do have a range of molar mass here of the compound. Remember though that that pretty much is the approximate molar mass of this compound. And that is one of the three things that we need to actually calculate the molecular formula here. In this particular case, we are not given the empirical formula. So we do need to calculate that ourselves, and that will allow us to get to the molecular formula. So we got our empirical formula we need to calculate. We will also then need to calculate the empirical formula's molar mass. And again, the third thing that we would need here to calculate the molecular formula is the approximate molar mass, which again in this case was given to us as a range. And we'll talk a little bit more about that later as to how we kind of go about that range there. Let me just kind of clean this up a little bit. I kind of ran off the screen there as I'm writing. Find here eraser. There it is, I think. All right. Rewrite this so we can actually keep it on the screen maybe. And we have like a 90 to 95 grams per mole. Perfect. So now we can actually see it. All right, so we should start our process here. So we're going to convert and calculate our empirical formula. So taking the grams of nitrogen, which is 1.52 in this case, using the molar mass for nitrogen, which is found on the periodic table of 14.01 grams per mole, we will then calculate our moles of nitrogen. We'll also do the same thing here for oxygen. So we're going to take our 3.47 grams of oxygen, again returning to the periodic table there to get the molar mass of oxygen, which is 16 grams per mole. All right, let's grab here a calculator. We got our 1.52 divided by 14.01 grams. Will give us our moles of nitrogen here. It looks like we got something like 0.10849 moles, and I'll take it out to a few digits here. We're going to do the same calculation here with our calculator, 3.47 grams divided by 16, getting us 0.2168 moles of oxygen. At this point, once we convert it to moles, we do want to divide by the smallest number of moles, which in this case is the nitrogen moles. So we're going to divide everybody here by 0.10849. Also divide the oxygen by 0.10849. Obviously that's going to give us a 1 for nitrogen, dividing our 0.21688 divided by 0.10899. Gives us 1.999, which is pretty close there to 2. So remember that is close enough to round to the whole number. Remember that if you do get a number that's like 1.5 or 1.33, that is too far to round. But this case, it's obviously right close to 2. So basically we hit 2 whole numbers here, and that means that we will get our empirical formula of NO2 in this case for the empirical formula. So we could check that off our list here. That is one of the 3 things that we need to calculate the molecular formula. We now want to calculate the molar mass of our empirical formula. Again, we would go to the periodic table to do that. So we got a nitrogen at 14.01 grams per mole, plus 2 times the molar mass of oxygen, which is our 16 grams per mole. Again, grabbing my calculator here, doing a little calculation. 2 times 16 plus 1401. Gonna get us a number. It's gonna be 46.01 grams per mole. We can now check that off our list. That's our second thing that we need, our molar mass of our empirical formula. We already have the third thing that we need, which is the molar mass of the compound, which again was given to us in the problem. In this case, we have a range that we could use. So I'm going to start here first with kind of the middle of the road there in terms of the range. So something like maybe 92.5 grams per mole as the molar mass, using, again, kind of the middle of the 2 numbers there. So taking that middle road of 92.5 grams per mole, divided by the empirical formula's molar mass, in this case of 46.01, going to give us approximately here about 2.01, which obviously is very close to 2 in this case. Now let's say you didn't kind of go middle of the road here in terms of the molar mass, but chose the lower end of the molar mass range, which is 90 grams per mole. we can take that number and divide it by 4601 grams per mole. And in this case, it will give us something like 1.96, which again is fairly close to 2 in this case as well. Okay, let's say that we decide not to take the middle of the road or the low end, but we'll take a look at what would happen if we chose the high end of the range, which would be in this case obviously 95 grams per mole. So if we took our high end at 95 grams per mole and divided by our 4601 grams per mole, which is our molar mass of our empirical formula, that also is going to give us, well, approximately 2 as well. Looks like we'll get here 2.06, which is pretty close to 2. So you can see you took the low end of the range, the middle end of the range, or really even the high end of the range. You pretty much get a factor to multiply the empirical formula by 2. So you really could choose any number within that range. And again, when you're figuring out this factor, that's really the one place where it's okay to kind of round to a whole number, trying to figure out the factor to multiply our empirical formula by. So we're going to multiply our empirical formula by that factor of 2. So that's going to give us N2O4 as our molecular formula in this case. So now that we have the actual molecular formula, which should tell us exactly how many elements are there, or atoms of those elements, we could actually answer the last part of the question here, which is what is the molar mass of the compound, or the molecular mass. And we'll do that 2 times 1401 grams per mole for our 2 nitrogens, plus 4 times 16 grams per mole for our 4 oxygens in this case, giving us a molar mass of approximately here, in this case, it's not really approximately, but giving us a molar mass of, let's see here, 92.02 grams per mole, which as we see is fairly close to our middle number that we chose originally. So this is our true molar mass to 4 significant figures in this case. Once again, we needed to get the empirical formula. Once we had the empirical formula, we needed the molar mass of the empirical formula. And once we had the molar mass of the empirical formula, using the molar mass of the compound given to us, we're able to figure out our factor that we needed, which in this case was 2, no matter which one you chose, to figure out our molecular formula. Okay, let's take a look at another one here. Here it is. All right, so in this case, we have phosphorus oxide contains 43.64% phosphorus, 56.36% oxygen, and has an approximate molar mass of 283.89 grams per mole. So once again, in this case, we're actually looking for both things, the empirical formula and the molecular formula. We obviously have the approximate molar mass of the compound given to us, which is very helpful in terms of calculating the molecular formula. But first we want to start with the empirical formula. So remember, when you do have percentages given to you, you want to quickly just kind of add them together, make sure that they do equal 100%. That allows you to know that you pretty much got all of the elements that are present. Once you have that, you can assume that you have 100 grams of each of these total. And what that does is actually keep the percentage the same number as the grams. So for phosphorus, instead of 43.64%, we could assume we have 43.64 grams of phosphorus to start with. And same thing for our oxygen, instead of 56.36%, we could assume we have 56.36 grams of oxygen. Once again, the first thing we want to do to figure out our empirical formula here is to convert these guys now from grams to moles. We would go to the periodic table, look up the molar mass of phosphorus, and also the molar mass of oxygen. So phosphorus looks like it is 30.97 grams per mole. And for oxygen, it is still 16 grams per mole. All right, let's grab a calculator here, and we're going to convert these guys from grams to moles. So for our phosphorus, taking our 4364 divided by 30.97, going to give us, in terms of moles for phosphorus, a 1.4091. We're going to do the same thing here for the oxygen, taking 56.36 grams of oxygen divided by 16, getting us 3.5225 moles of oxygen. Once again, here to calculate the empirical formula, which is what we're doing, we're going to divide by the smallest number of moles, which looks like it is the phosphorus here. So we're going to divide everybody by 1.4091. That is going to give us a 1 for the phosphorus. And when we do that for our oxygen, taking our 3.5225 divided by 1.4091 gets us about 2.4998, which is 2.5. Taking this as our empirical formula gives us PO 2.5. Once again here, we ended up with a non-whole number, 2.5, too far to round. So we need to figure out that factor. So again, 2.5 times 1 is 2.5. 2.5 times 2 is 5. That means that we actually want to multiply it by the factor of 2 and not what is commonly done by a lot of people, multiplied by 5. So remember, we want to actually multiply by the factor, not the result. So we're going to multiply our empirical formula here by 2, gives us P2O5 for our empirical formula at this point. Once again, remember, multiply by the factor, not the result. A common mistake, everybody multiplies sometimes by 5 in this case instead of 2. Now that we have the empirical formula, we're going to get our molar mass of the empirical formula, which really is the second thing that we need there to calculate the molecular formula. Taking 2 times our 3097 for our phosphorus plus 5 times 16 for our oxygen, going to give us a molar mass of our empirical formula there of, looks like, punching it in here, like it will end up being 141.94 grams per mole. So 141.94 grams per mole is our molar mass of the empirical formula. And once again, that is the second thing that we need to get to the molecular formula. And the last thing that we need is molar mass of the compound, which was given to us as 283.89. So taking that molar mass of the compound, dividing it by the molar mass of the empirical formula, 141.94, going to give us a factor to multiply our empirical formula by, which in this case looks like it will be a factor of, I think, 2 here in this case. So we're going to multiply our empirical formula by that factor, which is 2. And that will give us a molecular formula in this case of P4O10. That would be our molecular formula, P4O10, to go with our empirical formula of P2O5 in this case. So once again, the steps that we want to follow here is, in this case, we need to calculate the empirical formula. So we figured out our empirical formula and divided by the smallest number of moles, making sure that we got a whole number for our empirical formula for each of the subscripts. Once we got that, we got our molar mass of our empirical formula, taking the given amount, a molar mass of the compound divided by the empirical formula's molar mass, once again gives us that 2, which is the factor that we needed to multiply our empirical formula by to calculate the molecular formula. All right, well, that should wrap up the last couple of examples from Chapter 8. Hope this was helpful, and we'll catch you on the next one. Bye-bye.